Spatial transformer for 3D points. Motivations. Many works aim at defining the convolutional operation on a point cloud. A point convolution can be defined as a weighted sum of the features of the point itself and its neighbors in a neighborhood, n sub I. K nearest neighbors is a common way of defining the neighborhood of 3D points. The features are learned using deep networks, layer by layer. Earlier layers capture lower-level features, while later layers capture higher-level features. Previous work on point cloud processing applies the same original point cloud for convolution, and the local neighborhood stays the same for each layer. When the neighborhood is the same for every layer, point cloud processing is not optimal. We propose having a dynamic neighborhood for each layer. At each layer, we learn multiple different transformations of the original point cloud location. Because of the transformation, at different layers the neighborhood of each point is different. We learn these transformations from point cloud location P and feature F. The desired transformation should capture geometric transformation of the 3D shape for semantic understanding. For example, for two samples of the table category, yellow graphs exaggerate the surface, while red graphs exaggerate the table base. Now, we introduce three proposed spatial transformers: affine, deformable, and projective. Affine transformer. We first apply the affine transformation A to the original point cloud to get the transformed point cloud G. Then, apply K nearest neighbors to get the neighborhood n sub I on the transformed point cloud G. For each subgraph at layer T, we can perform a point convolution to get the subfeatures of this graph. We finally concatenate all subfeatures to form the final output feature. Projective transformer. We retain everything else, but perform the transformation on homogeneous coordinates. The deformation transformer is the combination of an affine transformation on the point cloud and a deformable matrix D sub I that gives every point the freedom to move. We learn the deformable transformer from both the point cloud location and its features. Since AP is the affine transformation of the point cloud, we project feature F to three-dimensional space as deformable matrix D sub I. We evaluate the performance of the spatial transformers on three tasks. Since we propose a transformer module, we add the transformer to existing work without changing other components such as network architecture. We first conduct experiments on the ShapeNet part segmentation dataset. For the point-based 3D point convolution method, we observe improved results when applying transformers, compared with its fixed graph counterpart. For the sampling-based point convolution method, the deformable transformer also shows performance gain compared to the fixed graph baseline. Our transformers also outperform other state-of-the-art methods. Visualization of the segmentation results show that spatial transformers give better fine-grained details. The second task is semantic segmentation on the large-scale Stanford 3D indoor scenes dataset. Again, we show performance improvement with spatial transformers. Our spatial transformers also outperform state-of-the-art methods. Visualization of the segmentation results suggests that combining a network with transformers will give better results. The final task is 3D detection on the Kitty dataset. We use the same architecture as VoxelNet, but add additional spatial transformer blocks to it. We observe improved results on both bird's eye and 3D detection with spatial transformer. Now we analyze why spatial transformers boost the performance. Here we visualize learned transformations on the ShapeNet part segmentation dataset. We observe that for different samples in a category, the transformer tries to align geometric transformation for semantic understanding. For a rocket, corresponding graphs in red exaggerate the wings of the rocket for easier learning. Graphs in orange exaggerate the body of the rocket. Similarly, for different samples of a table, corresponding graphs in red exaggerate the table surface, while graphs in orange exaggerate the table base. We also provide a local view of the transformation. When zooming in, we find the raw point cloud is actually imbalanced. This can be hard for neighbor search based on k-nearest neighbors. With our deformable transformer, the point cloud becomes more balanced. The box plot showing the variance of data also suggests that transformation helps reduce the variance of the point cloud. In conclusion, we propose novel spatial transformers on a 3D point cloud for altering the local patch in different point cloud processing tasks. We propose one linear spatial transformer, the affine transformer, and two nonlinear spatial transformers, the projective and deformable transformers. Spatial transformers can be easily added to existing point cloud processing networks. Transformers boost the performance by aligning geometric transformation for semantic understanding. They also help improve the performance by making the point cloud more like balanced sampling.